As covered in part 1, when running ACI in the cloud, we just need to focus on the logical network configuration. And we may then follow the same 5 steps we learned about when covering the on-prem ACI version. There are a few minor differences, so let's take a quick look at what changes. After we finish the initial APIC configuration, we always have 3 default tenants that are automatically created in ACI: Infra, Common, and Management, each with their default VRFs as we learned before. In the case of the Infra tenant, its automatically created VRF is called Overlay 1, and although we don't need to do much about it, you should know by now that in the case of the on-prem environment, this is used to transport VXlan traffic between leaf and spine nodes from multiple tenants. In the cloud, this is very similar. Let's take AWS for example. Your APIC is running on the Infra tenant, which translates to the account you use in order to deploy your APIC in a specific region. As part of such automated deployment, a VPC was created to provide your cloud APIC with cloud networking services behaving as the Overlay 1 VRF. After you deploy your cloud APIC service, you can verify the automated creation of such VPC by going to the corresponding section in your AWS console. All the private IP addressing was deployed based on your initial settings, which automatically created the necessary CIDR blocks and subnets. The Infra tenant will have the main networking services deployed based on the connectivity option you choose in the setup wizard, which may include transit gateways or CSR 1000Vs serving as hubs in a hub-and-spoke topology with BGWs, or even for inter-cloud connectivity purposes. It will also have the BGP autonomous system based on your setup wizard configuration, which will represent this ACI site. The same will happen in Azure, automatically creating the Overlay 1 VRF as a VNet in this case, running in the Infra resource group, and deploying Azure Network Load Balancers or NLBs and CSR 1000Vs for VNet peering, or just deploying CSR 1000Vs serving as hubs if a hub-and-spoke topology with VNGs is preferred. Once Cloud APIC is configured, we can start our logical network configuration by creating a tenant just as we know it. When running ACI in the cloud, each tenant is either a different account, in the case of AWS, or a different resource group, in the case of Azure. Azure can use different subscriptions or share the same subscription for different tenants as long as different resource groups are created. As you create your different tenants in your ACI deployment, Cloud APIC will automatically configure all the necessary network settings on each tenant account or resource group across different VPCs or regions for each cloud. This is why you must allow Cloud APIC to have the right privileges for each workload tenant account or resource group. If you're running Cloud ACI on AWS, this is very easily done through the tenant CloudFormation template, which is available in an S3 bucket created by the initial deployment on the Infra account. The same thing can be done in Azure with a single command that Cloud APIC provides, as we will cover in the configuration chapters. Once we have our tenants, we have to create at least a VRF for each of them, as you already know. However, there is a slight difference. If you remember, cloud providers assign private IP addresses automatically using CIDR blocks, subnets, and availability zone associations. Therefore, when running ACI in the cloud, you will need to create a new construct called Cloud Context, which will include these settings for the region where you want this VRF to run on. Additionally, the Cloud Context configuration will include the connectivity method you want to use on this VRF, which in the case of AWS would be either BGW and CSR or Transit Gateway. The same thing will happen in Azure, changing the connectivity method options to VNGs and VNet peering as we've covered before. Let's take a look at an example, starting with AWS. If we have 2 different VRFs or VPCs in the same region that need communication between them, and we wanted to use CSRs and BGWs as the option to interconnect them, Cloud ACI would automatically deploy and configure those. The same would apply on Azure, and in both cases we can communicate such VRFs automatically through Cloud ACI even if they exist in different regions. Now, since there are bandwidth limitations per tunnel for both BGWs and VNG implementations, we may want to use Transit Gateway on AWS or VNet peering if using Azure. In the case of AWS, for example, Cloud APIC would automatically deploy the Transit Gateways on the Infra tenant and configure each workload tenant VPC attachment with its corresponding routing entries on each VPC routing table. Again, no manual configurations would be needed. The same would apply to Azure by using VNet peering, with a slightly different automated implementation, In this case, the infra VNet would peer against the workload tenant VNet, and routing between spoke VNets would be facilitated by a couple of CSR 1000Vs behaving as network virtual appliances, or NVAs, as it is commonly known in Azure. Both CSRs would be balanced by an Azure Network Load Balancer, or NLB. Again, all this is automated and happens in the infra tenant. Therefore, you don't need to worry about it in terms of configuration. The workload VNets, or VRFs, will also be automatically adjusted by creating user-defined routing, or UDR, with the corresponding routing entries. In any case, Cloud ACI allows us to mix and match based on the needs and feature availability of the different cloud regions. For example, if running on AWS, if transit gateway peering is not available in a specific region, and you still need to provide global connectivity there, you could connect that specific region through BGWs and CSRs to communicate with the rest of the regions, providing automated, secure, and consistent networking services, even when using different cloud-native networking options. The same would apply to Azure, where we could deploy a mixture of VNet peering and CSR plus VNGs depending on your needs. This is mainly what changes when creating a tenant. As you can see, creating the cloud context and linking it to your VRF is a critical and powerful additional step, since it contains the region, CIDR block, subnet, and connectivity model you want to use. However, its configuration is very simple, as you will see in the next chapters. Once we're done with the tenant, we have to create an application profile just as we are used to, and then we create EPGs and contracts. If you remember, when running ACI on premises, there are two main types of EPGs, regular and external ones, which are also known as L3-out EPGs. When comparing this to the cloud, we also have regular or cloud EPGs, external EPGs, and there's a new type of EPG called service EPG. No matter which one you use, remember that different EPGs need a contract if they want to communicate. Let's start with the regular EPG. If you remember, when running on-prem, we can statically assign an EPG to a port, VM, or switch, or you can use microsegmented EPGs and ESGs to dynamically map an endpoint based on a specific attribute or attributes through a selector. Now, if we compare that to the cloud, cloud EPGs are always microsegmented, meaning that endpoint to EPG mapping is dynamically performed based on attributes you define as an ACI admin through the use of selectors. We can set the selectors to match a specific region, availability zone, IP, tag, or multiple elements at the same time. Once cloud instances are created, ACI will map the instance to its corresponding EPG based on the selector configuration. Behind the scenes, ACI will transform that EPG configuration into an AWS security group, if you're running an AWS Cloud APIC, or an Azure ASG and NSG configuration, if you're running an Azure Cloud APIC. Then, just like L3-out or external EPGs on-prem, we have external EPGs in Cloud ACI, which automates the creation of a security group or NSG entry with the prefix you include in the selector, and then the corresponding rules when you create your contract. For example, if you wanted to create an external EPG representing the internet, you would need to add a quad 0 selector, just like in the on-prem version. Finally, as of ACI 5.12, you can also use service EPGs, which can help you establishing secure and consistent communication with PaaS and SaaS services. Unlike regular cloud EPGs, which communicate infrastructure as a service instances and VMs, service EPGs may communicate PaaS and SaaS services as well, which may include cloud-native services such as Azure Storage and S3, managed cloud-native services such as AKS, EKS, Azure SQL, RDS, and more, or even third-party services, all available directly from Cloud APIC. It is important to mention that Layer 4, Layer 7 services can also be inserted using service graphs as part of your contract defining Cloud ACI, automating the deployment of cloud-native services like load balancers and even third-party ones, in addition to just redirecting traffic, as we will cover in Module 4. As long as you remember these main two differences we covered today as part of your logical network configuration, you should be pretty much ready to connect anything running in the cloud. As a summary, Cloud ACI allows you to learn and configure one network while automatically deploying and enforcing those changes anywhere. Not only does this reduce the time it takes to learn and configure cloud-native networking constructs, routes, security policies, and many more, but it also normalizes your operational model without sacrificing any cloud-native services and with no hardware nor hypervisor dependencies. But this is just the beginning, since in Module 5, we will cover how to extend automation and normalize cloud operation even across different cloud providers by using multi-site orchestrator, which runs on top of Nexus dashboard. Although Cloud ACI and multi-site orchestrator provide great amount of built-in automation, it is important to mention that they both integrate with infrastructure as code options through our partnerships with Terraform and Ansible, to name a few. This same model can also help extend your on-premises ACI deployment to any of these clouds if you need to. Through multi-site orchestrator, we can automatically extend MPBGP and VXlan connectivity over VPNs or physical dedicated connections like Direct Connect and Express Route, while providing complete visibility, telemetry, and AI-assisted proactive operations when running Nexus Insights as well.